Hi, we are Team 5 and we've put together a virtual project that is an amalgamation of this semester's work. We combine aspects from each lab, including sensing, localization, path planning, and controls to complete two tasks in a virtual environment due to the remote nature of this semester. To do so, we utilized Tessie, a Unity-based environment that communicates with ROS via a ROS bridge to simulate a typical city with realistic obstacles with which we test our autonomous car. The first task is a race where the goal is fastest lap time without a collision. The second is an obstacle avoidance task that tests whether our simulated vehicle can avoid obstacles that it does not know is on the map and can only detect using the sensors provided on the vehicle. To accomplish these tasks, we used a particle filter to localize our robot, a trajectory algorithm to find the ideal path given our map, and a pure pursuit controls to drive the car. To elaborate more on our first task, the timed race, here's Andrea.
Thank you, Kevin. As can be seen with the previous slide, we were given a known map and path to follow, and our goal for this challenge was to make our robot follow said path in the shortest amount of time possible and with the least collisions possible. This new environment had real physics, so we had to account for that in our algorithm creation. This challenge was the challenge that used the integration of several of the labs we had already done with some minor modifications. First, our car had to localize itself in this world, so we integrated the localization module. The race car that we were given had two LiDARs, a hood and a trunk arm, but due to ease of integration and knowing that we could localize effectively with just one, we decided to forego the data of the second. We also noticed that out of the box, our particle filter was transmitting data to our car at a rate of 4 Hz. This greatly affected the performance of the localization and path follower. So in order to increase this frequency, we decreased the number of particles and corresponding beams per particle used. Once localized, we moved on to building a trajectory for our car. We were to follow the given path, while also taking into account the new abilities of our car to drift, crash, accelerate, and decelerate, as well as to flip if colliding with certain conditions. To this end, we began constructing a trajectory with a waypoint at every corner or turn we had to make. This, paired with the functionality of our path follower, was a good start to getting our car to complete the race. As can be seen, there was an overlapping section of our path with the beginning and end. Our original path follower made it so that our car would follow the closest segment to it in general, as long as it did not regress in the trajectory. This meant that with the original path follower, our car would immediately try to turn towards the goal when launched, so we implemented some changes to it. We implemented a change in our algorithm that would only allow us to see a constrained amount of trajectory segments in front of us, usually the one we were following, and up to the next two in order to account for the overlapping paths. This allowed for the car to still traverse the path effectively, while adhering to the order of the trajectory we initially set. Finally, in order to better adhere to the path given, the added physics to the environment, we implemented a change in speed when turning corners. We used the fact that we made a waypoint at every corner or turn in order to implement our algorithm, limiting the maximum speed of our car when approaching a distance within 35 meters of the next waypoint allowed our car to slow down in order to make the turn and minimize drifting of collisions. After traveling 20 meters from the waypoint to its next one, the maximum speed was once again restored. Now we will have Gongi talking about our steps for implementation of the obstacle avoidance challenge.
Thanks a lot, Andrea. Now, as you can tell from this cute graphic, the next part of the final challenge was obstacle avoidance. This was a unique task because we weren't given any suggested approaches. Our task was to drive down a straight road while maneuvering around rectangular obstacles detectable by LiDAR. The 11 obstacles were each spawned in a random position and orientation, so a hard-coded path wasn't possible. The car had to be reactive to the environment in real time. Our goal was to drive at 8 meters per second. Our first approach was unsuccessful but showed promise. Intuitively, the displacement vector from a LiDAR point describes the direction to drive in towards the obstacle. If we drive in an orthogonal direction we call the guidance vector, we avoid collision. If we take the average guidance vector from every point, we get a good heuristic for the safest direction to travel, shown in red. This proved useful at driving away from the barriers, but we didn't make much forward progress along the road because the car just drove in circles. Clearly, we need some sort of navigation then. So we use a simple form of pure pursuit since we only need to look at one segment from the start point to the end point. So we take the localized pose given by our particle filter, intersect a circle with radius 18 meters, our look-ahead distance, with the segment. The further intersection point is our target, and the car's angle to this target, shown in the red arrow, informs a P controller which will control the robot's steering angle. This will veer the robot towards the segment. So what happens if an obstacle is in the way? For each potential steering angle, we'll compute two scores. The close score counts the number of points in a rectangle of width 2 meters, about the width of the car, and height 8 meters, the distance traveled by the car in 1 second. The far score counts the number of additional points if the height is extended to 16. In the shown steering angle, there are 3 points in the close box and 0 points in the far box, leading to a score set of 3 and 0. And here are 2 more examples of score sets. So here's a recap of our overall procedure. First, for 120 possible steering angles, we calculate the score set, and then we sort first by increasing close score, and then break ties using far score. Take a look at the lower right for an example. After sorting the angles, we find only angles in the green region will have minimal scores. But Pure Pursuit wants us to follow this red arrow. Our best choice is to publish the black arrow, which is the closest direction to the Pure Pursuit controller angle, which still has the best safety score. Now Andy will present our tests.
Thanks, Gongi. Most of our testing for our robot was tuning lots of different parameters incrementally by hand. So we had various different parameters that needed to be tuned. As you'll notice, we divided them up into ones related to our slower around the corner speeds and faster speeds. So each one has its own KP value, its look ahead distance, and the slow values had its own special parameter that determined basically how soon we wanted to slow down and speed up after the corners. So as you'll notice, we had to try a bunch of different slow speeds because we wanted to maximize the speed around the corner that would allow us to get the fastest time. So some slower speeds like 8 meters per second would allow us to finish the course. However, it wasn't necessarily a speed that we were gunning for originally. So we would try to keep increasing the speed while minimizing collisions. So a good speed that we eventually settled on was about 13 meters per second, which allowed us to finish 4th place in the race, fortunately. You'll notice that a bunch of the faster parameters we didn't change very much, mainly because we were trying to max out the speed. So we actually set the straightaway speed to be about 100 meters per second, which is unrealistic, but it caused the robot to go as fast as it could during those straightaway portions. So most of the variability came into account for the corner turning. We also had to iterate on the trajectory many, many times alongside these other parameters. So we actually kept modifying the trajectory up until our final attempt at the race course. One of the big things we had to take into account was shifting our trajectory so that we could account for drift in our particle filter. We could notice patterns in where the particle filter's localization would drift, and we could adjust for that accordingly using our trajectory since we were given the map originally. We also tried breaking the turns into various waypoints, which would allow us to avoid trickier obstacles, kind of like the final pull at the end of the race that many teams were struggling with. So we could cause the robot to slow down even more at those trickier spots by breaking the trajectory into more than one waypoint for each corner. So here is our final result. This was our final attempt at the race. So the robot ramps up and it's going as fast as it can along the first straightaway. And it makes the turn successfully. We do kind of run over corners a little bit, we noticed, but this was also variable given how our particle filter was doing in this particular run. So it's going fast again on the straightaway. This particular corner, we kind of broke into 2 waypoints to allow us to not hit some of those poles we were struggling with originally. This is an example of where we had to drag out the trajectory even more so that we could account for where our particle filter ends up. And here we added multiple waypoints and successfully completed that turn to finish the race in about 48 seconds. With respect to the obstacle avoidance, we had many similar parameters that we needed to tune because we built it off the same sort of pure pursuit model. So we needed to pick the maximum speed we could get the car to go. We need some KP values that would successfully allow us to navigate the obstacles correctly and follow its original path smoothly. And we had to set the look ahead distance as well. So these were parameters that we needed to tune many, many times incrementally. But there were some other ones as well. So for padding around the obstacles, this was dependent on what segment of the LiDAR we were using and how far we wanted to be away from the obstacles. So at first we were struggling with the robot cutting the corners too close when it was turning to avoid the obstacles, and we wanted to figure out the best distance that would allow us to avoid them successfully. We also messed around with the starting location a bit. When we started in its original position, we were having difficulties with the robot hitting a lot of obstacles on its way to try to make it onto the actual trajectory of the course. So we tried starting it in the center of the map and allowing the robot to go straight away, and that seemed to show a tiny bit of improvement. So now I'll hand it off to Nadia to talk about future improvements of the race car.
Thanks, Andy. To ensure the robustness of our final project, we started by developing a framework for our algorithms. So far, we have implemented localization as provided by the staff to allow the robot to know its location on a given map. But to also find a trajectory and follow it, Andrea described our path planning approach. Working in tandem at all times, these nodes are highly dependent on each other and form a framework for autonomous racing. As Gongi explained, the obstacle avoidance was reactive to the environment real time and interfered whenever the car is at risk of running into a detected object. This is crucial for real-world applications of automation. Imagine Nona is buying a fully autonomous car. Crashing is much worse than being slightly late for her meeting. This familiar example illustrates that the obstacle avoidance and safety controller are a priority in the development process. Though in this virtual simulation we couldn't inflict tangible damage, in the future we can improve by testing a few different approaches for collision avoidance to stay conservative and prevent any damage to the car. And even more importantly, the poor passenger. Despite the extensive testing done with a variety of different parameters that Andy summarized, we could improve the integration process of the nodes by tweaking parameters and iterating through more testing combinations. This will take us even closer to our goal of achieving an automated agent. To allow the agent to interact better with its environment, we can add additional cameras besides the LiDARs to extract other types of information that might be useful. In this simulation, we were given access to left and right hood cameras. These two vantage points give information about object location and give us perspective, just as our eyes allow us to see in 3D. We also have access to the distance to objects by a depth camera. A technique called stereo visual inertial odometry, or VIO, combines visual and inertial measurements extracted from these sensors to produce an optimized SLAM approach. Another great technique is to use semantic segmentation, as we outlined in Lab 4, to incorporate knowledge about nearby objects into the agent's actions. In the simulation, we did not need to produce an RNN to give us those results, but were given the ground truth in the segmentation camera view. Knowing which object is the road can inform the car about drivable areas. Conversely, other labels can show that the car is too close to obstacles and must alter its trajectory. Both of these techniques will not only allow to achieve a more precise and consistent localization, but also to better the object detection and collision avoidance algorithms. These are important in keeping Nona and, if you remember her newly bought autonomous car, safe. Thank you for listening and supporting us through these difficult times. It has been an exciting experience, and we largely owe its success to you, the staff.